In this lesson, we are going to combine the concepts that we learned so far in order to get a better understanding on why the RC circuit behaves as it does. In the previous lesson, we learned the behavior of the resistors and the capacitors. For resistors, we determined that the equation that describes its behavior is the following. The current in the resistor R1 is equal to the voltage across its terminals divided by the resistor value. In the case of the capacitor, we learned that the rate of change of its voltage, which is the derivative, is equal to the current flowing into the capacitor divided by the capacitor value. Once we understand the behavior of the components, it is easier to understand what happens when we connect them together. In the plot, we can see in orange the voltage of the capacitor. In blue, there is the voltage in the resistor, and at the bottom we have the current. At time 0, the voltage for the capacitor is 0. That makes the voltage across the resistor 1 volt because it is the input voltage minus the capacitor voltage. As consequence, the current in the resistor is 0.1 milliamperes, which is 1 volt divided by 10 kilo ohms. The current that flows through the resistor also flows into the capacitor. This makes it increase the voltage. But as the voltage increases, the voltage in the resistor decreases. Therefore, the current decreases as well. And if the current decreases, the capacitor will start charging slower. The same process repeats over and over and over until the voltage of the capacitor is the same as the input voltage, and that makes the current 0. Now let's put together the equations that we know for each component. The current of the resistor is the input voltage minus the voltage of the capacitor VC1 divided by the resistor value. The current of the capacitor is given by the differential equation that we learned before, but here is slightly rearranged. One important thing to notice is that the current of the resistor and the capacitor are the same because they are connected one after the other. If we replace the equations for the currents, we get the following equation. After simplification, we can rewrite it as follows. This equation is telling us that the derivative, which is the rate of change of the capacitor voltage, is defined by the difference of the input voltage and the capacitor voltage, and the value is scaled by the inverse of the resistor and the capacitor value. Let's see how this circuit behaves when the input voltage is not constant. In the following simulation, we can see in orange the input voltage. This is a pulse wave that changes rapidly from -1 volt to 1 volt. In blue, we can see the capacitor value. For these specific values of resistors and capacitors, we can see that when the input voltage is larger than the capacitor voltage, this last one increases, trying to get close to the value. When the input is less, the capacitor value decreases. As we increase the resistor value, we can observe that it becomes more difficult for the capacitor voltage to reach the input voltage. With a larger value of resistor, the output voltage becomes like an average of the input. If we decrease it, we can observe that the output voltage becomes closer to the input voltage, but the sharp transitions are softened. Removing these fast transitions is what makes an audio wave to sound darker. As a summary for this lesson, we derived a mathematical model of the RC circuit based on the equations of the resistor and the capacitor. This equation shows, in a simple way, how the values of the components affect the simulation results. We learned what's the mechanism that makes this circuit act like a filter. And last, This equation it's a very common first-order differential equation that shows up when modeling many natural systems. This concludes the first part of this course, and I hope you have now a basic understanding on how the circuits work. In the next part, we will go deeper into the theory and the methods used to analyze more complex circuits.